Hello everyone. Today we continue with inverse trigonometric functions, and I will teach you examples with derivatives and integrals. Here are the derivatives one more time and the related integrals. When we differentiate arc sine x, we get 1 over root 1 minus x squared. And this is when x is between -1 and 1, strictly, because otherwise in the denominator we get 0. Related to this derivative is antiderivative. If we integrate 1 over root 1 minus x squared dx, we get arc sine x plus c. Differentiating arc cosine. Arc cosine x prime is same thing with negative in front, same interval. And when we evaluate the integral on the right side, sometimes we can evaluate this like negative arc cosine if we want. If for some reason we want, we can we can evaluate this integral by writing arc cosine x with negative plus c. Usually we use arc sine. Now arc tangent x prime is 1 over 1 plus x squared. This is true for all x. Arctangent is defined everywhere. And the antiderivative related to this is integral 1 over 1 plus x squared dx. We can evaluate as arctangent x plus c. And now arc cotangent x derivative is here the opposite expression, and we can evaluate the above integral also like negative arc cotangent x plus c if for some reason the situation is such that we have to have arc cotangent. Okay. We don't do the inverse secant and cosecant. We don't work with their derivatives. So these are the 4 important cases which we consider. Now, examples. I want to start with this. Take the function fx, which is arc sine x plus arc cosine x. And I want to differentiate this function and see what is the derivative. These two functions have both a domain between -1 and 1. And because I'm writing derivatives, I shall take open interval. What is f prime? Arc sine prime, which is 1 over root 1 minus x squared, plus arc cosine prime, which is -1 on the same root. And we see that this derivative is 0 over the given interval. We know from Calc 1 that if a function has derivative 0 over some interval, the function is constant. So f(x) equals constant. Let's write this here explicitly. Arc sine x plus arc cosine x equals c, when x is between -1 and 1. It's very easy to compute this constant. Now this equation will be true for the closed interval, also, but we just need 0. So we take x to be 0. Arc sine 0 is 0 because sine 0 is 0. Arc cosine 0, what is this? This is pi over 2 because cosine pi over 2 is 0. So when we plug x equals 0 in this equation, we get 0 plus pi over 2 equals c. That's how we compute c. And we come to a very interesting identity. Arc sine x plus arc cosine x equals pi over 2. And this is true between -1 and 1. This function is constant, and it has this value. Here we have our identity. Okay, continuing further, another example. What about arctangent, arccotangent? Let's take the function fx, which is arctangent x plus arccotangent x. For all x, define. The derivative will be 1 over 1 plus x squared plus -1 over 1 plus x squared, again 0. So our function is constant for every x. Constant. So let's write this. Arc tangent x plus arc cotangent x equals c for every x. And again, let's take x to be 0. Arctangent 0 equals 0 because tangent 0 equals 0. Arc cotangent 0 equals what? Equals pi over 2 because cotangent pi over 2 is 0. So in our equation, we get again 0 plus pi over 2 equals c. So c is pi over 2. And we have this identity. Arc tangent x plus arc cotangent x equals pi over 2 for all x. Let's put this in green also. Nice identity. Okay, another example. I shall take some examples from the book. Here is number 22. We have a function y equals inverse tangent x squared. Okay, so this is the other notation. We write either arctangent or inverse tangent this way. And now we want to find the derivative. We have to differentiate the composition. So we need to follow chain rule. For the inverse tangent, if we have inverse tangent of some function u, and u is function of x, we have to go with the chain rule. So it will be dy dx will be the inverse tangent u du times du dx. And this will be 1 over 1 plus u squared. That's what happens when we differentiate with variable u times u prime du dx. So here is the rule. That's a general rule. If we have inverse tangent of u and we want to differentiate, we go u prime over 1 plus u squared. Why not put this in green also? Important formula. Excellent. Okay, returning to our problem, u is x squared here, so y prime will be x squared prime over 1 plus x squared squared. So this will be 2x 1 plus x fourth power. That's it, our derivative. Okay, now moving to number 26. I want to do this one. Here y equals arc sine 1 over t. And let's say t is bigger than 1. So 1 over t will be less than 1 and positive. And the function is well defined. Let's find now the derivative. Here we have to differentiate again using chain rule. Let's write general formula. If we have arc sine u is a function of x, to differentiate, we have to go du dx. So this will be 1 over root 1 minus u squared, differentiating with respect to variable u, times u prime. So that's u prime over root 1 minus u squared. Another green formula, important rule for differentiation. And then we apply it to our case. U will be 1 over t. You can differentiate. U prime will be negative 1 over t squared. Okay, if you feel uncomfortable with this derivative, you can write u t negative first power, then t negative first power prime will be negative 1 multiplied by t negative second power rule. And that's exactly negative 1 over t squared. Okay, in our problem we have y prime, u prime here on top, negative 1 over t squared, and the denominator 1 minus 1 over t, all this squared. We can write this like negative 1 over t squared, and here below we have 1 minus 1 over t squared. This can be simplified. One way to do it is just bring t squared inside. It will get inside and become t fourth power. I can write it this way. T fourth power multiplied by 1 minus 1 over t squared. So this will be negative 1 over root t fourth power minus t squared. Or we can actually pull now t squared outside and write it also this way. Here t squared minus 1. T is positive, bigger than 1. So that's the answer. Either this or this. Okay. This was 26. And now I'm jumping to 32. I think this is quite interesting. Function h of t is defined this way. Inverse tangent. Let's put variable x. More familiar to work with x. Inverse tangent x minus square root x squared plus 1. Just look at this. And we want to find the derivative. Okay. Inside the arctangent, the function we call u. So we have to go u prime over 1 plus u squared. Separately, we shall compute u prime, and we shall compute 1 plus u squared, and then assemble everything together. So what is u prime? U prime, this is x minus, I shall write it this way here, x squared plus 1 power 1/2, all this prime. So for the square root, we use power, to use power rule. So this will be 1 minus 1/2 x squared plus 1 negative 1/2 times 2x by chain rule, derivative inside the parentheses. We see that 2 cancels out. This will be 1 minus x over, I shall return to the root notation, x squared plus 1, like that. And because later we had to divide this by something, it's good to write here common denominator. To put it like quotient. It will be root x squared plus 1 minus x over root x squared plus 1. So this expression is our u prime. Now what is 1 plus u squared? Again, we do this separately. 1 plus u squared, look at u, this will be perfect square. So we have to go x squared minus 2 times the product of the two terms, and plus second term squared, which will give you x squared plus 1. Okay, we can simplify. This will be 2 times 2x squared, so I can then just put 2 in front. 1 plus x squared minus x root x squared plus 1 with 2 in front. This will be our denominator. So now we do u prime over 1 plus u squared. U prime, this was root x squared plus 1 minus x over root x squared plus 1. And now we have to divide by, what is it in here? I shall write first separately, 1 over 2, 1 plus x squared minus x root x squared plus 1. By the way, 1 plus u squared we can factor, and this will be very good to factor immediately. We can factor this way. We can pull out the root this way. Here, taking the root outside. In the parentheses, we have root in the place of 1 plus x squared and minus x. After factoring it this way, we see that many good things will happen. So again, u prime over 1 plus u squared will be, just rewriting, x squared plus 1 and a second, make this better, minus x over root x squared plus 1. And here below we multiply by 2 root x squared plus 1 and multiplied also by root 1 plus x squared minus x. These are factors. And you can see how this factor and this factor will reduce. And what will be left on the top 1, and here we have factor 2, and the 2 roots multiplied will give you x squared plus 1, like that. which I can write like 1/2 1 over x squared plus 1. This is our derivative. H prime is 1/2 1 over 1 plus x squared. That's our answer. But I don't want to stop here, because what you see in the answer, that's the derivative arctangent, and we can construct a new identity. I can write this like 1/2 arctangent x prime, or I can put inside this constant. And we have two functions with the same derivative, so they differ by constant. Let's write this here. Inverse tangent x minus square root x squared plus 1 equals 1/2, let's use this notation again, plus c. This is true for all x. Both functions are defined for every x. And we can compute c. Again, let's take x to be 0. On the left side, we get inverse tangent 0 in first position from the root 1 of -1 equals arctangent of 0 is 0 equals c. So that's what is c, inverse tangent of -1. What is this? If we call this, we can write that tangent c equals -1, and the inverse tangent takes values between -π/2 and π/2. For what angle is this happening? When the tangent will be -1? Well, c will be -π/4. So that's how we compute c, and here is our new identity. Inverse tangent x minus root x squared plus 1 equals 1/2 inverse tangent x minus π/4. Green box again. And this is true for all x. So these derivatives are in the book for purpose, to teach such identities. Okay, continuing further, I have for you another challenging derivative. This is number 30. Y equals now arctangent root 1 minus x over 1 plus x. Now, because of this square root, we have restrictions. X should be between -1 and 1. That's over this interval, everything is defined perfectly well. 1 minus x will be positive, 1 plus x will be positive, and the ratio will be positive. So we differentiate again. This radical we call u, and the derivative will be u prime over 1 plus u squared. Again, we had to do u prime separately and 1 plus u squared separately. So here we have 1 minus x, 1 plus x square root. This is power 1/2. Differentiate this. And we have 1/2, 1 minus x, 1 plus x, -1/2, 1 minus x, 1 plus x prime. Continuing the next line, negative 1/2, I shall write now again like square root, and I have to flip these two, so it becomes square root 1 plus x on top, 1 minus x, and the derivative of the ratio here, what will this be? Let's see, using the quotient rule, on the top we have negative 1 times 1 plus x minus 1 time 1 minus x, and all this over 1 plus x squared. On the top, when we remove parentheses, this will be negative 1, negative x, another negative 1 plus x. So x will cancel out, and this derivative here will be on top negative 2, and divide by 1 plus x all is squared. So here I'm writing it negative 2, 1 plus x all is squared. So we can simplify, reduce by 2. We're just working on u prime, still on u prime. So u prime will be negative. To cancel out, we have square root 1 plus x, 1 minus x, and here 1 over 1 plus x all is squared. This will be on the top. I can even write it this way. It will be more convenient to divide further, like negative root 1 plus x, and separate the two roots, root 1 minus x times 1 plus x all is squared. Now, what is 1 plus u squared? This is 1 plus, remember what is u? On the top, 1 minus x, here 1 plus x, and adding common denominator, this is 1 plus x plus 1 minus x over 1 plus x. This is 2 over 1 plus x. So now y prime, which is u prime over 1 plus u squared, will be dividing these things. Negative root 1 plus x over root 1 minus x, 1 plus x. I can make this better. 1 plus x squared multiplied by 1 plus x over 2. And what happens? We can reduce by 1 plus x, and it becomes negative root 1 plus x, root 1 minus x, 1 plus x, like that. And believe it or not, we can reduce even further, because 1 plus x, I can write root 1 plus x squared. So we reduce by this radical, and y prime becomes negative 1. Oh, I forgot my 2. There will be 2 root 1 minus x times root 1 plus x, which we can put together negative 1, 2 times common root 1 minus x, 1 plus x. Now, you know from algebra, difference plus sum, the numbers, this will be first squared minus second squared, so this will be negative 1 over 2 square root 1 minus x squared. I shall write this again. Our derivative is negative 1 over 2 square root 1 minus x squared. And this we can recognize. This will be the derivative 1/2 arc cosine x. And we have two functions with the same derivative, which brings to another identity. This brings to arctangent, our original function, square root 1 minus x 1 plus x equals 1/2 arc cosine x plus c. This is happening in the interval with -1, 1. What is c? Just take 0, x equals 0. On the left side, arctangent 1, which will be pi over 4, because tangent pi over 4 is 1. On the right side, we have 1/2. Arc cosine 0 is pi over 2 plus c. So this becomes again pi over 4 plus c. Turns out c is 0. And another identity, this is arctangent root 1 minus x 1 plus x equals 1/2 arc cosine x. This is it. Another green box. So we are practicing derivatives, and at the same time we're learning very interesting things about the inverse trigonometric functions. Now it's time to do some integrals. And I shall choose from the book. The integrals that we're going to use were listed at the beginning, and we shall use them. Here I'm going to number 60. There is a group of group of problems with integrals, sorry. And number 60 is this. Integral with limits. Here below, -1 over root of 2. On the top, 1 over root of 2. And we're integrating 6 over square root 1 minus p squared dp. For some reason, the variable is p. It's unimportant. This variable inside the integral with limits is unimportant. It's a dummy variable. You can write x if you want. Now, it's easy to recognize this integral. If we put the 6 outside, we recognize arc sine. So this will be 6 times arc sine p between -1 over root of 2, 1 over root of 2. So this will be 6 times arc sine 1 over root of 2 minus arc sine -1 over root of 2. These values now we have to recognize. Arc sine of 1 over root of 2. For hot angle, the sine is 1 over root of 2, or you can multiply top and bottom by root of 2. It's 2 over root of 2. So that's like 2 over root of 2. And this is -2 over root of 2. Sine of pi over 4 is 1 over root of 2, and sine of -pi over 4 is the second value here. So this will be 6 pi over 4 minus -pi over 4. 6 negative plus pi plus pi over 4 is pi over 2. And this becomes 3 pi, the value of our integral. So important to figure out arc sine 1 over root of 2 is pi over 4. Arc sine -1 over root of 2 is pi over 4. We're looking for solution between pi over 2 and pi over 2. Okay, another example, 62. Evaluate integral from 0 root of 3 over 4 dx over 1 plus 16x squared. It resembles arctangent, but it's not quite the same with this denominator. However, 16x squared we can write like 4x all this squared. And we see that it's good to make a substitution. U equals 4x. So making this substitution, we get du is 4 dx. The x is 1/4 du. Now we have to change the limits. When x is 0, u is 0. When x is root of 3 over 4 times 4 is just root of 3. And we put 1/4 outside, and inside there will be du over 1 plus u squared, and that's 1/4 arctangent u between 0 and root of 3. And this will be, 1/4 in front. This will be 1/4 arctangent root of 3 minus arctangent 0. And tangent 0 is 0. Arctangent root of 3, we found this before. That's pi over 3. So the final answer is pi over 12. Now I want to show you a shortcut which saves time. By the way, before I continue, pay attention how I'm organizing my work with the substitution. In a separate place. Separate some space like that, like this box, and you do this work here. Then solving the integral, you write equals, different answers. And when you read this solution, the work here in the box does not interfere with the rest of the work. Now the shortcut. Starting from the beginning, 0 root of 3 over 4, the x 1 plus 16x squared. So we already discovered that 16, this is 4 squared. I'm writing the x 1 plus 4x squared. Now I can divide by 4 and multiply by 4, and this 4 on the top I can bring behind d, and this can be written 1/4 0 root of 3 over 4 d 4x over 1 plus 4x all this squared. And I can regard 4x like a variable. Instead of writing a new letter, just think of this like u. And integration gives you 1/4 arctangent 4x now here between 0 root 3 over 4. And evaluating these limits, you get 1/4 arctangent root of 3 minus arctangent 0. So that's the same thing. That's pi over 12. What is the advantage? You don't use different letters, you don't play with du dx, you don't change limits. This saves time. You have to do one or the other, either the shortcut like this or complete substitution with the details. And remember, when you make a substitution and you change the limits, you don't return to the old variable. Now, another one, this is 64. Evaluate integral 0 pi over 2. On top here sine x, below 1 plus cosine squared x dx. Now, again it looks like arctangent because of this cosine squared here, and we can think about substitution, but I want to show you the shortcut. We shall go later and solve trigonometric integrals, so this will be important. We have that d cosine x is negative, just a second, negative sine x dx. So this product sine x dx I can write like negative d cosine x, like that. Here d cosine x, and below 1 plus cosine squared x. Same limits. And now you can think of cosine x like variable. You can think of this like u, without explicitly making a substitution. And we integrate immediately. This is u over 1 plus u squared. So you get negative arctangent of this u, which is cosine x, between 0 and pi over 2. Evaluating, we have negative arctangent cosine pi over 2 minus, because of the negative sign, becomes plus arctangent cosine 0. Cosine pi over 2 is 0, arctangent 0 is 0. So this is 0 plus arctangent of 1, which is what? Arctangent of 1? This is pi over 4, because tangent pi over 4 is 1. So this is our answer, pi over 4. The next one, 68. It's without limits, exponential 2x on top, and below square root 1 minus exponential 4x dx. Okay, a natural substitution will be exponential 2x, to call it u, because what we have here is exponential 2x squared. However, I prefer to go with the shortcut. I shall go like this. First, I'm writing this is the same exponential 2x dx, and here I'm organizing 1 minus exponential 2x squared. So I shall regard exponential 2x as variable. Now I want to bring it behind d. Divide and multiply by 2, and put 2 here. So exponential 2x d 2x will be d exponential 2x. Regarding 2x as variable, because we have eu du, that's d eu. Continuing with my integral. So this will be now 1/2 integral d exponential 2x over root 1 minus exponential 2x all this squared, and that's arc sine exponential 2x, and plus c and nothing else. No new letters and no returning to old variable. By the way, if you go with the substitution u equals 2x and work the integral, which you can do for practice, then you have to return to x. That's important. Now, to finish today's lecture, I want to mention some important integrals, because we often meet such integrals. Like, what if we have integral 1 over a squared plus x squared dx? I can make simple plastic surgery and make it look like arctangent. Factor a squared. So I write it this way here: a squared 1 plus x squared over a squared dx. And this can be written 1 over a squared integral 1 over 1 plus x over a all this squared dx. Now, I shall write 1 over a squared like 1 over a times 1 over a. And one of them I will bring behind d. So the integral becomes 1 over a integral 1 over 1 plus x over a all this squared dx over a. And look at this. Regarding thinking about x over a like u, that's arctangent. So this is 1 over a arctangent x over a plus c. This is one table integral that you need to use from time to time. I shall write it again. 1 over a plus x squared dx. That's 1 over a arctangent x over a plus c. Why not put this in a box, green box, because it's one very important integral. It happens often. For example, let's say you have integral 1 over x squared plus 5 dx. 5, this is root of 5 squared. Let's make a good 5 here. Root of 5 squared. So I can write immediately a is root of 5. 1 over root of 5 arctangent x over root of 5 plus c. Look at this. And similar things we can do when we have 1 over 1 plus, let's say, b squared x squared dx. Then I can write this 1 over b, 1 over 1 plus bx squared together, and then I divide by b, multiply by b, dbx behind d. One bit on top, one below, and this becomes 1 over b arctangent bx plus c. What about the arc sine? Integral 1 over root a squared minus x squared dx. Doing similar cosmetic surgery here, putting a squared, this actually becomes arc sine x over a plus c. Do it yourself. And if you have integral 1 over root 1 minus b squared x squared dx, multiplying top and bottom by b, you can write this like 1 over b arc sine bx plus c. Think about this and use these integrals in practice. I shall put here green boxes, green boxes. Okay, enough for today. With this lecture, I'm finishing the sequence of lectures on inverse trigonometric functions. Next, we go to the rule of L'Hopital.